In this section, we'll define the arc length function. One thing that we should keep in mind is that for every curve in space, we don't have just one parameterization of that curve. So every curve in space can be represented by more than one vector functions. So for example, if we have a space curve that is represented by the vector function vector r1 of t that is equal to the vector with components t to the square and t to the third, where 1 is less or equal to t less or equal to 2. And then if we use a different parameterization, for example, if we set that t is equal to e to the u, where u is another parameter, and then the vector function vector r2 of u that is equal to the vector with components e to the u, e to the 2u, and e to the 3u, where 0 is less or equal to u less or equal to the natural log of 2, represents the same curve that is represented by the vector function r1 of t. Now, suppose that we have a curve that is represented by the vector function vector r of t that is equal to f of t times the vector I, plus g of t times the vector j, plus h of t times the vector k, where a is less or equal to t less or equal to b. Then the parametric equations for that curve will be x equals to f of t, y equals to g of t, and z equals to h of t. And we can define the arc length function s of t. So we denote the arc length function s of t. And this is equal to the integral from a up to t of the magnitude of the tangent vector evaluated at u times the u. And this is equal to the integral from a up to t of the square root of dx over du to the square plus dy over du to the square plus dz over du to the square times the u. And therefore, this arc length function, if we have a curve C, it represents the length of the curve, the length of the part of the curve C that lies between the vectors RA and RT. Now let us differentiate these two sides of the arc length function with respect to t. So we'll have that the derivative of the arc length function with respect to t is equal to the derivative with respect to t of the integral from a up to t of the magnitude of the tangent vector evaluated at u times du. And using the fundamental theorem of calculus part 1, we have that the derivative of the arc length function with respect to t is equal to the magnitude of the tangent vector evaluated at t. Now, this formula is sometimes very useful in order to parameterize a curve with respect to the arc length. And the reason that we sometimes choose to parameterize a curve with respect to the arc length is because the arc length arises naturally from the shape of the curve and does not depend on any particular coordinate system. So the arc length is something that is internal to the curve and does not depend on any particular coordinate system. So we sometimes choose to parameterize a curve with respect to the arc length. Now let us see an example about that. We are asked to find the arc length function for the curve vector r of t that is equal to 2 times t times the vector I, plus 7 minus 3t times the vector j, plus 7 plus 4t times the vector k, and then we parameterize the curve with respect to the arc length starting from the point with t equals to 0. In order to find the arc length function, we'll first need to evaluate the tangent vector. So the tangent vector is equal to the vector with components, the derivatives of the position vector. So we have derivative of 2t with respect to t will give us a 2 times the vector I. Derivative of 7 minus 3t with respect to t will give us a negative 3 times the vector j. And then we have plus The derivative of 7 plus 4t with respect to t will give us a 4 times the vector k. And therefore, the derivative of the arc length function with respect to t will be equal to the magnitude of the tangent vector, and that is equal to the square root of the sum of the squares of the components of the tangent vector. So we have square root of 2 to the square plus negative 3 to the square plus 4 to the square, and this is equal to the square root of 4 plus 9 plus 16. So that is equal to the square root of 29. So let us now try to find the arc length function for the curve. So let us denote the arc length as S. So the arc length S is equal to the arc length function with respect to t, and that is equal to the integral. Now, we are given that the starting point is where t is equal to 0, so we have from 0 up to t of the magnitude of the tangent vector evaluated at u times the u. So this is equal to the integral from 0 up to t. And the magnitude of the tangent vector, we just found that is equal to the square root of 29 times the u. And evaluating that, that gives us that this is equal to the square root of 29 times t. So therefore, the arc length function S of t is equal to the square root of 29 times t. And we can now use that S is equal to the square root of 29 times t, solve for t, so t will be equal to 1 over the square root of 29 times S, and use that to substitute that in the curve to reparameterize it with respect to the arc length. So substituting t equals to 1 over square root of 29 times S to the original equation will give us that the vector equation of the curve, so vector r of t with respect now to S, will be equal to 2t. So we have 2 times the 1 over square root of 29 times S. So t is equal to 1 over square root of 29 times S. So we'll have 2 over the square root of 29 times S times the vector I. And then we have plus 7 minus 3 times t, so 3 times S divided by the square root of 29 times the vector j. And then we have plus 7 plus 4 times t, so 4 times S divided by the square root of 29 times the vector k. So this is the way that we can reparameterize a curve with respect to the arc length.